Coding in progress.
All right, welcome everyone. So we're continuing with the hands-on machine learning book. Today's kind of an exciting day. So chapter 9 is the last chapter in part 1 of the book. So this is the end of our Scikit-Learn journey. And next week, we're actually going to start talking about deep learning. So really, part 1 and part 2 of the book are almost like two completely different books in one. So really, this is kind of like finishing book 1, and then next week we're starting book 2, even though it's in the same physical book. I found that there's quite a bit more information in chapter 9 in this week's chapter than there have been in the last couple of weeks. So while the title is Unsupervised Learning, and last week we talked about one unsupervised learning algorithm or technique for dimensionality reduction. We're going to talk about clustering, a little bit about density estimation, anomaly and novelty detection, and then in the process of that, there are some things that are mentioned, like the expectation maximization algorithm and maximum likelihood estimates. So if we have time, we'll go a little bit deeper into those topics. But as usual, what I wanted to do is just start off by asking people in the room, people in Zoom, if you had any particular questions, something that you didn't fully understand the explanation, something you wanted to know deeper. If so, then I'll make note of that to make sure to cover it when we get to those sections. So I'll pause for a second. Any particular questions?
Yes.
All right. So if no specific questions, then I'll just go through the book kind of chronologically from the beginning to the end. All right. So one thing I'll mention just off the top is this chapter does go through these different unsupervised learning techniques fairly quickly. I thought that the author did a good job mentioning in multiple places here are applications where we actually use these things. But also know that these unsupervised learning techniques sometimes are used as a component inside of a bigger machine learning pipeline. So they mentioned a couple of them, but for example, clustering is something that just may be this small little piece inside of some other process. So an example I can give you, somebody just this past week was talking to me about when they're fine-tuning LLMs. Right now, a lot of people are using this GRPO algorithm, and what you do is you give it a batch of sample completions, and you have some way of scoring them, for better or worse. Okay, and the GRPO is a reinforcement learning algorithm that will modify the weights to give higher preference to the kinds of completions that you rated higher. As a process of doing this, one of the things that people have noticed is that they get less diversity in the kinds of completions that the LLM will give you. And so you can see this where if you, for example, are doing some complex math problem and you do a lot of completions, you do 500, you do 1,000 completions, you'll actually kind of see where you get to the point where it's just repeating and you're not actually getting anything new anymore. Even though you have different random number seeds, you're just still just getting. Whereas if you look at the model before they did the reinforcement learning, you will continue to get like 1,000 different ones and so on. So there's this one research paper where somebody said, hey, what we could do is we could cluster the high scoring answers, and if we see that there's sort of like a main cluster, we'll give more weight to the ones that are outside of the main cluster. Okay, I'm vastly summarizing it, but the point of this is just that clustering was just this like barely mentioned thing in the paper because it's just like, hey, we want to do this clustering. They're just assuming that people know that this is something that can be done. Okay, so obviously that will make more sense as we go through this whole thing, but just wanted to kind of highlight that sometimes all you need is one of these techniques. Okay, somebody says, I want you to cluster my customers into, a few different personas. Then you're just doing clustering. But there's other times when these algorithms end up being subcomponents in something bigger. All right. Um, so hopefully, since people didn't have questions, the basic idea of unsupervised learning, the big hard problems that we solve are all pretty much supervised learning. So how do you fold proteins? How do you, um, I don't know. And then a lot of them, end up using some form of like self-supervised learning in order to get, more data. But ultimately, unsupervised learning is where you don't have labels. And so, simple diagram in the book says on the left, we're doing classification because we have 3 different labels. And on the right is here's a bunch of data, no labels, you just see these dots. And then what kinds of information, what kind of patterns could you observe from just seeing these data points? Okay. And so the first thing we're going to talk about is, hey, you could do clustering. You could say this data seems lumpy. There seems to be a group over here. And then do you decide, is this one big group, or is this 2 groups, or is this actually 4 groups, one over here, one, whatever, okay? But the idea is that these are all techniques that you can do without any labels. All clustering algorithms use some form of distance. So what I say over and over again is as soon as you hear the word distance, then you know that scaling matters. So every single clustering algorithm, scaling matters. If you had some data and it was price of house in hundreds of thousands of dollars, and you had something else like number of bathrooms that's 1, 2, 3, this would not be great for clustering because the price of the house would completely dominate your distance metric. So you do need to scale them so that they're on similar scales. Not really discussed in the chapter, but there are some advanced distance measures used that are not just like Euclidean distance. But this doesn't matter. Whatever measure you use, it's still going to be this problem that if you have something in the hundreds of thousands and something else that's 1, 2, 3, 4, there's going to be a very disparate sense of near and far. So you want things on a similar scale so that the distance in each of the features is similar.
So the distance can be calculated for any of the features, or do they take only one feature? I mean, if you have several features, and if you calculate the distance for this feature, the cluster comes out like this. If you take some other feature, the cluster might change.
Yeah, so most of the time when we talk about calculating distance, we're just going to treat all dimensions simultaneously.
Okay.
So if you see here, most of the examples, just because they're easy to visualize, are 2-dimensional. And so you're just taking that diagonal and you're saying the distance between any 2 points. In 3 dimensions, it's just, that 3-dimensional distance. And then it's a little hard to visualize, it's a little hard to understand. But if you have 75 dimensions, it's the you sum up the squares of all of the components and you take the square root. It's the Euclidean distance. But like I said, there are some algorithms that have options to use different distance that's not Euclidean, but it really kind of doesn't matter whether you square it or don't square it or whatever you do. If one of them's 100,000 and the other one's 3, the 100,000 is going to dominate the distance. That's the problem. Let me just check the chat real quick. In unsupervised learning, do we need to drop the target column or the columns in which can cause leakage similar to supervised learning? So generally speaking, when we're doing unsupervised learning, we don't even have a target, so we don't have to worry about dropping it. If you were using unsupervised learning as a subtask, then yes, you would generally speaking apply that same principle of you're not going to use that target because when it comes time to actually making predictions, you're not going to have that particular value available to you. Yes, it's a good point. All right, a few other notes I have here. One is that the geometry of the clusters that you actually have depends on whatever your use case is. So in this case, with the iris petals, you can see that this blue cluster is not circular, okay? And so one of the things that we'll talk about when we talk about the different algorithms is what sort of measurement, what sort of comparison do they use, and that's going to bias the geometry of the clusters that they find. So in particular, the first algorithm, k-means, does circular or spherical clusters. And so k-means will not necessarily do a great job when you have clusters that are more stretched out like this, okay? And then you can have clusters that are even weirder where they're like squiggly, like a worm, and that will require a very different algorithm. In high dimensional spaces, we often don't know what the shape of our clusters is. So it's not like you can just say, oh, because I have this shape, I'm going to use this algorithm. But sometimes we have some intuition whether they're sort of compact and possibly approximately spherical, or whether we think they might be very wispy, spread out kind of a things or whatever, right? So if you had a natural phenomenon, anything where you're looking at like two different species of animal, two different species of plant, they're probably somewhat compact. If you were looking at, I don't know, some kind of genetic interactions or whatever, then it's possible this is a very not circular kind of a relationship. And so that would be like the little bit of domain intuition that you can bring to the problem. The other thing I will mention is that some algorithms require that every single point belong to a cluster, and other algorithms do not. And that can also affect your choice down the road, because if you have really noisy data with a bunch of outliers, you might actually get more accurate clusters if you ignore all the weird data points. And so again, when we talk about k-means, it's an algorithm that uses every single data point. So if you said, for example, this iris data set, well, these are for on the right-hand side. We're going to make clusters, and let's just say we guessed correctly and we wanted 3 clusters. If I add one data point way, way out here to the upper left, okay, that point has to be included in one of the 3 clusters, and it is going to skew the final clusters that we come up with, because some cluster is going to include that, and it's going to yank that cluster way up and to the left. We'll see there's other algorithms like dbScan where they'll just simply say, nah, that point seems weird, I'm not going to use it, and then that might allow it to have its clusters be more naturally defined just by the close together points. All right, so with that preface, let's talk about k-means. So essentially, yeah, question.
So you were saying that, yeah, k-means doesn't do well, like the circular or spherical, like kind of. So k-means is doing the circular or spherical, like not for those clusters which are like a lot wider. What's stopping us from taking that wider clusters as like a big circle and considering that means is there some kind of optimization or something which is like stopping us? I'm asking if
yeah, no, that's a great question. So what's stopping us from just using circular clusters? So in the case of like this data, and again, there's not much separation between the blue and the green, okay, but let's say there was a little bit. If I drew a circle around the blue ones, we're actually fine. It doesn't matter that I did a circle instead of something more oblong. The problem would be if there were a blue cluster here and say a red cluster right next to it, and they were both long. Then if you drew a circle around either one of them, it's going to overlap with the other one. Yes, so if you really thought, and later in the chapter we have some diagrams where they have some cases where you have 2 clusters that are next to each other, and if they're not round, then k-means will tend to just lump them together in the same cluster. Oh yeah, no, that's fine. Yeah, you can try and shift your seat over. Yep, yeah, but so that's the
probably skewed. There's a lot of room.
Yeah. Yep. But so that's the thing, and yes, not going to go into detail on many different algorithms, but I will be highlighting specifically for the algorithms where there's some sort of geometric aspect. Okay. So hopefully people had a chance to read the chapter. I'm not going to go through the exact algorithm for k-means, but what it does in the assignment step is it assigns each sample to the cluster that it's closest to that cluster centroid. Okay, so if a temporary interim definition of a cluster has 25 data points, it doesn't really matter if some of those data points are close to you or if some of those data points are far from you. The only thing that matters in k-means is how far are you from the center of that cluster. Okay, and so if you look at this diagram, this Voronoi diagram that was included in the book, and you look at these little, it's a little hard to see, but the white circles with the X's in them are the centroids for each of the 5 clusters. These lines separating the different clusters are going to always be exactly halfway between the 2 dots. Okay, that's how we know where to draw the lines. Is because, again, if a point were slightly to the left of this line, it means it's closer to the yellow center than it is to the orange center. And then similarly over here, if a point were slightly to the left of this line, then it means it's closer to the pink center than the yellow center. Okay, and so that's the definition of how far are you from one cluster to the other, and that's the reason why we end up with these circular or spherical clusters, is because all we care about is your distance from the center of the circle or sphere, or hypersphere in higher dimensions. Okay, and so in this case, intuitively, I might say, because this is low dimensional, oh look, the pink cluster seems very compact, the green and gray ones seem very compact, but the yellow and orange ones seem more spread out. So if I were, as a human, drawing the clusters, I might do the separation between the pink and the yellow closer to the pink one, because the pink ones seem to naturally be really close. And since the yellow ones are spread out, I will give it a little more benefit of the doubt. K-means does not have that kind of intelligence into it. It just says, no, I'm going to assume all clusters implicitly have the same sort of density, where we're just going to use radius as the way of defining where clusters, bump into each other and separate. Okay. The cool part of the algorithm is that by alternating between updating the centers and updating the assignments, that you actually find really good centers. Okay. K-means is very intuitive if you already have the right centers picked to begin with. The hard part of clustering is finding the centers to begin with. And so the k-means algorithm is very good at doing that, and it also is an extremely fast algorithm. So whereas it could theoretically, if you had 100,000 data points, it could take you, 100,000 iterations before the centers converged. In reality, it'd be like, oh, maybe it less than 10 or something like that. It's incredibly fast to converge. So that's why we see this as sort of your default clustering algorithm for a lot of people. Yeah.
So when you initialize k-means, is it that the centroids are first determined at random, and then as you move points closer to the centroids, they sort of move to adapt to where the data is?
Yes. So in fact, the next section is specifically about initialization.
Okay.
And so you might say to yourself, well, if I had data and all of the data was on the scale of 100,000, if I picked my random initialization between 0 and 1, that would be really terrible. On the flip side, if all my data is between 0 and 1, and I said, let's have my random data points be between 0 and 100,000, that would also be really terrible. So how do you really know where to pick your initial things? And so somebody figured out pretty quickly, oh, if I pick actual data points, then they have to be within the range of whatever the things. So the default thing is if you're doing k-means and you want 5 clusters, you just pick 5 random samples out of your entire data set. Okay, and it's guaranteed that they will then be in, so to speak, the box that all of your real data points live in. Okay, they won't necessarily be great, and so the book mentions that there's a k-means plus algorithm where instead of just picking points completely randomly, you pick the first one randomly, and then the second one you change the odds of a point being picked so that it's slightly greater if it's farther from the first point than if it's closer to the first point. And then for the third point, you want a point that's kind of far away from both of the first two. Eventually, you'll have enough that you can't necessarily actually be far away from all of them. But it just ensures that you're unlikely to accidentally get 5 points that are all in the same corner. That's not super likely to begin with, but it even just further decreases the odds. So common practice is you could get a bad one, and so the default for the Scikit-Learn implementation is they do the plus thing, and they also run k-means 10 times in a row and pick whichever one gives you the best results. All right. And because k-means is so fast, the good news is you can actually, under most circumstances, afford to run it 10 times, and it's still pretty darn fast. All right. But so that's the initialization and the thing, and usually, you can get unlucky. So you probably don't even, under most circumstances, need 10 initializations. 5 would probably guarantee that. One of them might be really terrible, but the others are unlikely to be. 10 is very safe, in my experience. Any other questions? Yeah?
So the initialization is one problem is fine, like the iterator part and the implementing, like the plus operation that is meant, and also the running k-means 10 times. The initialization is going to cover that, or it's going to cover the selection of that center point from other.
Yeah, the initialization is just about picking your initial points as centers.
Okay.
And the plus just means that instead of completely randomly, you slightly put your finger on the scale so that you tend to get points that are farther apart. Doesn't guarantee they're far apart, but they're. I'm not quite sure your question. Let me try answering it slightly differently, okay? So if in the regular k-means, if I'm doing 7 clusters, then I just say for I equals 1 to 7, pick a random point that I haven't already picked. And you do that 7 times. And so you can get any 7 points just completely at random, okay? In the plus algorithm, it says for I equals 1 to 7. If you have any data points already, do something different. So for the first point, you just pick it at random, okay? For the second point, it says now the odds of picking each point are rated based on how far that point is from the first point that you've already picked. Okay, I'm not giving you the specifics of it, but it says that if you had 99 more data points, for regular k-means, the odds of each point getting picked would be 1 out of 99, okay? In the plus algorithm, it says, oh, this point is super close to that one, and so now the odds are more like 1 out of 200, but the odds of a point that's really far away are maybe 1 out of 50 or something like that. So it's just saying any point's possible, but let's make it more likely to pick the ones that are farther away. And so then it just, kind of helps you avoid having 7 points that all bad luck just wind up in one corner right next to each other. Okay, let me just check the chat real quick. Okay, I'll repeat the questions. I think you guys aren't getting them all on the mic.
It's the online version of this book for this particular chapter, so it's completely different. So you can having hard time.
All right. Yes. Speaking of which, let me. I I think there's a visualization I didn't copy. Yeah. So this one is actually showing the k-means algorithm in process. So we have these 5 red randomly selected initial points, okay? And based on this, when you say for each of our existing data points, which of the 5 is it closest to, you wind up with this particular 5-way breakdown of all the points, okay? And so you can see, like, this green one is not a very good breakdown at all, all right? The other ones are actually not so bad, all right? So then if you say, what is the center of mass of all of the points that are currently green, you see that this x actually moves quite far to the right because all the points are actually located over here, all right? And then the other points don't really move that much, okay? But this green one moved a lot. Then in this next step, we say, okay, which of the centers are they closest to, including this moved over green one, and now the green one's starting to look better, but you can see it's still not in the center, right? Visually, it just looks wrong or whatever, right? With this one, if you then, again, just look at the center of mass of all the dots that are now green and the center of mass of all the dots that are now gray, what you see is just after 2 iterations, this green one looks pretty good to the eye. This gray one looks pretty good to the eye. And so this is, you know, some whatever. This is not exactly the hardest clustering job because the clusters are all fairly separated. But you can see just 2 iterations of changing the centers has gotten it to be pretty darn close. So it may not be 100% converged. Maybe they're going to, you know, wiggle another tenth or, you know, 0.05 slightly up, down, left, right, or whatever. But at this point, we're pretty close to converged after just merely 2 iterations. So that's kind of what the algorithm looks like when it's running. All right. The book also mentions that there are some variants, and they are available in Scikit-Learn. The accelerated one keeps track of some intermediate data, and it tries to avoid having to calculate the exact distance between each point and the centers over and over again. So in the example that I showed here, in the first step, we saw the green center moved pretty far, okay? But the other centers didn't really move all that far, and so it's entirely possible to say, for example, for these points that are here in the upper left corner, there's no way that they're going to wind up being closer to one of the other centers, just given how the centers moved. And that's the goal of this algorithm, is to try to identify as many points as possible where you're like, there's no way it has a different center, and it can just kind of do that a little bit faster. I'm not super familiar with the algorithm, but the other one that is helpful is this idea of the mini batch k-means. So if we have 500,000 data points and we're assigning these to a small number of clusters, let's say 7 clusters, do you think if we didn't use all 500,000, if we only used 10,000 data points, wouldn't we likely have approximately 1,000 or more data points in each of our 7 clusters? Probably. Okay. Now the clusters don't all have to necessarily have equal numbers of points. They don't have to be equally represented, but you could imagine, right? And so that's the idea behind mini batch. And it's possible that in one mini batch, you could even get some very bad information where you're missing data for cluster 6, okay? But when you keep running this over multiple mini batches, on average, that's gonna average out. So if you're familiar at all with gradient descent, you can have one bad batch that just gives you a really bad signal. And the thing is, if you're running thousands of steps or hundreds of steps, it doesn't really matter. It's gonna average out, and it's gonna be fine in the long run. So the book shows an example where they ran mini batch and they got a slightly different answer, but it ended up being a pretty good answer anyway. And it could be like I think they said 4 times faster.
So when you try to run this mini batches, can it like remember stuff from the previous batch and also this new batch? And like let's say if it has run this for like 10 times, does it remember what it has done for all the 9 times and the 10th time, everything? And does it like provide an optic, like how do you say, cumulative result instead of a new one every time, like maybe in the checkpoints, right? Sort of like that, or is it going to be like a starting over from the beginning kind of thing?
Yeah, so the question was about the mini batches. I actually don't know. I'm not super familiar with this algorithm. I'm fairly positive that the results in terms of like updating your centers and whatnot, that is just based on the current mini batch. It's not based on any accumulated data or anything like that. But whether or not it samples the mini batches with replacement, which means it's just a random set, each time, or whether it's a little bit more like when we do neural network training, we actually have mini batches and we ensure that we go through our entire training set in a random order, but we go through all the data in one epoch. I don't know if they actually manage epochs or if they just do random with replacement. I'm sure the documentation says, but that's the gist of it, is that your mini batch is going to give you a slightly noisy but reasonably good signal for where the cluster centers are each mini batch. And the more your data set is giant, the more you don't need the entire data set in order to estimate where the centers are. So
after a certain point, they will really stick right there, isn't it?
Yeah, exactly. Yeah, and you're not going to get the exact same answer because you never, in the end, use the full data set. But imagine in the extreme, you had 1 billion samples and you wanted 7 clusters. I mean, there's just no need for 7 clusters to have hundreds of millions of data points in every single center calculation. You probably could get away with something much, much smaller, just like in the thousands. All right, so one of the big issues with k-means is that you need to specify the number of clusters up front, okay? So one of the things you can do, since the algorithm is so fast, is you can just write a for loop and you can say, we'll try it for 3, for 4, for 5, for 6, for 7. That's all great, except the problem is, even if you do this and you get your results, it is not obvious which of those results actually got you better clustering, okay? In the textbook, they mention you can look at the elbow of this chart that has, the distances. You can look at the silhouette score. You can look at the silhouette diagram. In my experience, when you have real data, it's just not really obvious. None of those techniques seem to work as well as they do in the textbook example. Even in the textbook example, I think they had like 4 versus 5 clusters, and you could make a strong case that all of those indicators say you should use 4 clusters, but visually you look at it and you're like, I know it's 5. And then forget about it if your data is 200 dimensional and you don't upfront know how many clusters you're supposed to have. So what I will say is that these techniques will get you close. So like if it says 4, then maybe 4 is the best, maybe 5 is the best, maybe 3 is the best. And if your application is one like the one I was talking about, where we're just trying to slightly improve the diversity in our GRPO algorithm, then it doesn't really matter if you get your clusters exactly perfect. It doesn't matter if there are actually 10 clusters or if there's 9 or there's 11. So in a lot of applications, that's fine. But I just wanted to mention that, if you have a clustering thing and you should try to use these techniques, and you should see if there's a number of clusters that really jumps out to you as great. But it is entirely possible that you could have 1 million data points, high dimensional, and you're like, according to this data, 7 clusters is plausible, but so is 15, so is 22, and so is 39. Like, not even just like adjacent numbers, you know? That's often been my experience. It's like it's just not, you know. So I guess just I wanted to just say buyer beware. Okay. Um, for some use cases, it doesn't matter. If you're doing customer personas, is it super critical whether you have 6 clusters or 7 clusters? You know, probably not.
So if
Yeah.
there's no like mathematical or like measurable way of determining the best number of clusters or the best way of clusters, like how do people make decisions? Is it just like trick of the eye? Like I think it's this number. Like how do we?
Yeah.
Is there a reliable way to like make decisions, or is it just like different every time?
I welcome if anybody in the room or online has a better answer, but for me, I would say it's a little bit of domain expertise, and then a lot of the times um, there's 2 things you can do. You can try it and see how it works. So let's say you're doing clustering, but ultimately it's because you're predicting churn or whatever. So then you could say, does 4 clusters or 5 clusters actually give my downstream churn model a better result? Okay, that's the empirical, the good way. Otherwise, yeah, it's a little bit like you just, again, these techniques, like when you use I forget what the heck it's called, but the distance score, and you're looking for this supposed elbow or whatever, there is a number that will be the lowest. So like theoretically, like it is telling you like this is the principled way to pick that, and it's safe for you to pick it. I'm just saying that just because that's the principled thing to pick doesn't mean it's going to actually give you the best results on your downstream task. So let me just see this. Yeah, Richard.
I mean, for this question, I have an analogy because I'm from physics background.
Yeah.
Like if you have a point charge, like from I don't know high school physics or whatever, you have like a certain formula for the electric field or potential. If you have like 2 charges, then you have like a high order term like a dipole field or something. And then if you have 4, then you got like a quadruple field. And then it's like if you go higher order, then it kind of diminishes like in a certain way. So I mean that might be a quantitative way to like tell.
Sure.
Yeah. But like in terms of domain, like here's a kind of oversimplified thing. But if you were clustering customers and you found I got really good scores at 7 and at 15, practically speaking, it's probably easier to have 7 personas than 15.
Right.
So you're like, even if there truly are 15, and by choosing 7, we're clumping some of the personas, lumping them together, you know, it just 15 may just be too many, you know, and then maybe later on, if you get more mature, you might actually look at, hey, I wonder if some of our personas could be subdivided into 1A and 1B, and and you could try out the 15. But so there's reasons why, like, you know, initially, like you don't, you know, but whether you do 7 or 6, like I don't know. But yes, I just wanted to mention it because I'm just not aware. There's not for a lot of other things we try to give you black and white answers, and this is just one where there isn't. Yeah.
What about the feature correlation? What is the impact of correlation?
Again, it really depends on what you're doing downstream with these clusters. What we've said from like week 1 of this book is, oh, I see Ryan. Yeah, Ryan, go ahead if you want to add something.
Sure. Didn't want to interrupt, but I think one thing I want to point out is there's kinds of 2 different ways of doing machine learning and data science. And one of them is building models in order to describe certain things. So I have this data and I want to figure out patterns, and then you're using it as like imagine you're Amazon or something, and everyone's putting all of these listings for all these different things, and you need to group them based on this is clothing, this is a screwdriver, this is whatever. Um, there's not necessarily like some specific thing that we're optimizing for there, but it's very helpful for us to be able to say like, oh, look, here's this cluster. It's all of our tools, and here's our section. And so you can use something like this to kind of guide some of that decision-making process. And it's not as heavy on the mathematical side. It's kind of like, look, here's some proposed groups. What do we actually want to make this into? And Amazon is one example where we have strong human intuition for like this is closed, this is whatever, but often you have data where it's like I have no idea. I'm looking at random variables. What is the different possible groupings of things? And that can point you in the direction of like, oh, sometimes it behaves in this way, sometimes it behaves in that way. And so you can use it for description or you can use it for actual modeling. I'm trying to get the most accurate thing possible. And I think in general, clustering on that side is more of an art than a science, where it's like you look at this graph and people can interpret it totally different ways. There was a paper a while ago that it was something to do with reading the tea leaves, and it was basically saying we can cut this totally randomly a bunch of different ways, and you come to totally different conclusions. Um, so you can it's more art than science on that front.
Thanks, Ryan. Hold on. I think there's another hand raised. Yeah, Jacques, you have your hand raised?
Yes, can you hear me?
Yes, we can.
So I was working years ago with a data scientist for the project that I'm working on, and he used the technique of clustering to do blood pressures, and it was very interesting because it looked like, and I still, again, it was 5 years ago before everything, and it was kind of interesting how he would classify clustering as it to. He first wanted to try to make it easy, either not sick or sick, and we use blood pressure as a kind of like a way to do that. Could you say clustering is kind of like a sorting model, so that once you get in data, or even if it's large or small, but the more data you get in, it can just be driven into one of these two options, and then from there you can go further. Because the way he's doing it was like sick or not sick, using systolic and diastolic blood pressures, but then he said high risk and low risk. And that's what whenever I come across clustering, and that's what I kind of picture it as, kind of like a sorting model. They once you first start with two, then you can start with four, and then expand, 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 expand. And from there, that's where you can get your different clusters from that. Am I wrong in that thinking in a sense, or no?
Yeah, thanks for sharing that. I'll use a slightly different word. You sort of sort things and you end up binning them, right? So you're sort of sorting them, but then ultimately, after you're sorted, you sort of have your piles. Um, and so, yeah, and so like, thanks, Ryan. Also, so at the end of the day, whether Amazon decides all shorts are one cluster or it has one more cluster and it divides athletic shorts from dressy or whatever the technical term is shorts, like I don't think we really care whether there's one more cluster or one less cluster and they get lumped together, right? There's no real uh, super important ground truth to it. You just hopefully want the clusters themselves to be good, whatever the heck they are, however many they are. And then yes, if you ultimately have some downstream task, then everything we talk about in ML, the reminder is it's really the business metric that ultimately drives everything. So it doesn't matter whether we're talking about linear regression or clustering or deep neural networks or whatever. The goal is to build something that actually has business value. Um, and so uh, there is a way to say if you really cared about the difference between 5 versus 6 clusters, you could just run your whole pipeline with both and then compare the end results from the business perspective. So moving on, this next section, limits of k-means. So this is what we were talking about before. So here's actually the diagram. So what I mentioned is the geometry of k-means only considers distance. So it doesn't matter neighbors or other things like that. It's just the distance, and distance in all directions is equal. Okay, so this is why you get circular or spherical clusters. And here's the example where you have two elongated clusters sort of side by side. So spheres don't necessarily really line up well with these clusters. And so you can wind up with bad luck like this on the right, where you have a center here and a center there, and it's basically splitting it exactly wrong, you know. And if you just look at this inertia number, right, technically the inertia is lower for the one on the right. So if we were doing our principled thing and we're going for the lowest number, then this one is quote unquote better, but intuitively in low dimensions, you and I look at it, you're like, no, that's not right.
Taking the distance between the center and the edge, whatever is right next to it from there, or is it like Google Maps shows you right from one spot to the other? Like sometimes Google Maps does that, like where it kind of like shows you like if you are some kind of superhero who could fly, it takes you this long. But is it like taking that kind of distance, or is it taking the kind of distance like with the proper path, like in that line that is dividing those two?
Yeah, so by default, k-means, the question is about the distance. It's just using Euclidean distance, okay? So the expression that I know in English is as the crow flies, okay? So Google Maps, you know, should be looking at, well, you know, there may be a short way to get there, but if you're going to drive there, because there's a canyon in between you and there, you have to actually go all the way over here and then back and around, whatever, and it's quite far to get there. But no, k-means would always just be as the crow flies distance.
The aeronautical distance.
Yeah. So yeah, I could say more, but basically, just understand that if you have clusters that are sort of densely packed, and if you expect all of your clusters to be similar density size, then that's the optimal conditions for k-means. Doesn't mean you can't use it, but you just have to be a little bit careful. And again, in high dimensions, we wouldn't have this visualization. We wouldn't know that the one on the right is worse than the one on the left because the numbers actually, you know, report. So just wanted to be clear that it's not just that bad centers will always have bad numbers. In this case, here's a counterexample the author purposefully created where you see the one that we intuitively don't like is the one that actually has better numbers. And so if you had no visualization, you're just looking at the numbers, you would have picked that one. All right. And then I think I mentioned this before, but k-means is an algorithm that assigns every sample to a cluster. So outliers can kind of screw up your clustering. So you can think about potentially doing some work to remove outliers or choose a different algorithm or whatever, but just beware.
So we are computing distance here. Would dimensionality reduction help in this context, or is there anything about that, or?
I think the author mentioned, and there's an exercise at the end of the chapter where you can do dimensionality reduction to speed things up.
Yeah.
But I don't think it actually makes the clusters better. Okay.
But will they make it worse?
It's sort of the same rule with dimensionality reduction. So you purposefully do dimensionality reduction in a way that you hope is losing the least signal. Okay. But what you don't know is whether the signal you're losing is relevant to your problem or unrelated to your problem. And so last week I had mentioned in the worst case scenario, you might preserve 99% of the variance, but the thing you cared about was in that 1%. And so you could go from a so-so model to a model that is no better than random guessing, even though you kept 99% of the variance. So sort of the same idea here is that the clusters will still be the clusters, but they might not be helpful if you eliminated that 1%. Okay, but as a general rule, yeah, if you're keeping 99% of the variance, you're keeping 99% of the distance measures, and so you should get pretty similar clusters.
And have they done any benchmark studies, anything like any papers in that regard?
I'm sure there's been tons of papers I'm not familiar with, but yes, over the years. But
because this dimensionality reduction is a very old technique.
Yeah, you bring up, questions about dimensionality reduction. Honestly, I don't see dimensionality reduction mentioned in ML research papers very often. I would say not even 1% of the time, probably not even 0.1%. If you have the computing power, you're better off just using all the data rather than doing dimensionality reduction. So while in one sense dimensionality reduction is kind of alluring,
yes,
because you're like, oh wow, I can make this a lot smaller. The reality is, because you don't really know if what you're getting rid of is important or not, if what you're worried about is accuracy, so to speak, then these days computing is often cheap enough that people are just like, well, okay, yeah, buy a server that's a little bit faster and let the model run for a little bit longer and use all the data, versus go through this complexity of dimensionality reduction and then having to solve the problem and then having to go back and reconsider whether or not your dimensionality reduction hurt your performance and whether you're going to get rid of it or tweak it. You can just like fully eliminate that step. So it's very useful for visualizations, and I would say it's a pretty good tool to have in your tool belt if you are in a very constrained environment. So if you're at a university and you don't have that much compute and you want to do something on this giant data set, do some dimensionality reduction, and hopefully it'll allow you to make some sort of progress, have some sort of result. But if you're trying to actually do really interesting novel research, you're going to probably run into the issue where it's going to hurt your accuracy. And there's a joke that every research paper has to claim that they have the state-of-the-art best results, right?
Yeah.
And so if you do this dimensionality reduction and you hurt your results by 2%, then that could be the difference between whether you're so yeah, I just don't see it very often.
They no longer talk about it.
Yeah, and again, there is a little bit of a bias in this book where the author is going to talk about all the things that are available in Scikit-Learn, whether they're important or not. So that's where I'm saying dimensionality reduction is discussed, but maybe not actually really used that often, except for visualizations. For visualizations, all the time, because you and I can only see, for the most part, 2D on a piece of paper. All right, so there's an example here where the author does an image and they cluster the pixels based on the color. And so I thought this is a very nice visual, simple example to see how clustering, can be helpful in a when you have like 2D blobs, it's sort of like that's sort of a too trivial a way of defining clusters. So to me it's like not obvious that you would cluster pixels, but yes, you can cluster them by color. You can cluster any data by different attributes. And then they give another example that I really, really like. I'm very glad that he included it in the chapter. So it was clustering for semi-supervised learning. Okay. And so the example they gave was label propagation, the idea that you have clusters, and let's say you created 50 clusters out of your very large data set. You had your expensive person label just one item in each cluster, and then you labeled everything else in that cluster with the same label. So this is for your supervised learning task, okay? So if you're doing cats versus dogs, you found 50 representative images. You had your expert label those 50, and it turned out, 24 of them were cats, 26 of them were dogs, okay? And then every other image that's in each of those 50 clusters, you said, is a cat or dog just based on the one that was labeled. You don't know if those are correct or not, okay? But you're just using that, and that's a way to get you, let's say each cluster had, 1,000 images. You now have 50,000 labels, even though you only paid the person to label 50 images, okay? That's one technique that you can use. There's another technique which doesn't involve clustering, but pseudo labeling, where you can have a model that does the labeling for you, and there's not going to go into all the details, but there's different techniques where you can use confidence or you can use other things. And then active learning was also mentioned, and so one way the book mentions uncertainty sampling for active learning. But another way they can do it is, so for example, at work, we do a lot of work with images, and so I might have a model that's designed to find people, and then I might find that, this model seems to think a lot of dogs with curly hair are people. So knowing that in terms of active learning, I can then go and say, I'm going to find more sample images of dogs with curly hair and label them as not people and add them to my training set. Okay. But I bring this up because in textbook toy examples, life usually looks like, here is your training data. To a certain extent, Kaggle competitions look like, here is your training data. In the real world, one of the big questions is, should I change my algorithm? Should I do feature engineering? Should I do all of these different things? Or should I spend money getting more data? Money and time getting more data. And in fact, even in Kaggle competitions, you will sometimes see that, where they say, your challenge is to detect in these x-rays, cancer or not cancer. One of the things that some people will do is they'll say, I will go and I'll find other public data sets on the internet that are x-rays. It's just the sum of the distances, the Euclidean distances.
Was squared or just absolute value?
It's the Euclidean distances, the sum of the pointwise distances.
Okay, thank you.
Yeah, and so I think that if you just read an ML textbook, you tend to underappreciate that that's one of the big choices, is do you get more data? So even in Kaggle competitions, I don't know that I've seen a lot where it's like, oh, Bob won this competition because they did a really good job getting more data. It's not easy because the data you have is usually not identical to the data for your problem, and it may often not be labeled or labeled the same way or whatever. So there's issues, but nevertheless, clustering is one good example where you could do label propagation, and there's other techniques. And so as kind of a side conversation, a segue, I wanted to bring that in because that's what the real world looks like, is I have many different choices for how I'm going to expend my energy. And usually getting more data is very expensive, but if that is the thing that is limiting the performance of your model, then sometimes that is actually the best choice.
Can I ask a quick question about that?
Sure.
Is there ever a point where getting more data may like improve the model as far as like technical metrics are concerned, but it might be further from the result might be further from the truth because you're sort of manipulating the information that you're feeding into the system? Does that make any sense? Is there any trade-off there?
Can there be a trade-off with getting more data? I don't know that I've seen it the way you're describing. Certainly there's a trade-off in terms of time and money,
Sure.
right? So I have a dog and a cat detector and it's at 99%, and I get more data and I get it to 99.2%. And the reality is the economics of that extra 0.2 is just not worth it, right? So that's for sure a trade-off. But unless the data that you're adding has some sort of bias or whatever,
Right.
then it's not necessarily going to hurt your model performance. In my example about the curly-haired dogs, okay, it absolutely can be the case that if I add thousands of curly-haired dogs, then I might improve the performance on those dogs, but it might skew things so that my performance is worse on something else.
Sure.
So there's no guarantee that just adding data improves your overall everything.
Yeah.
Okay. And then we could just take it to the extreme, right? I have a training set and it has 100,000 examples of people and not people, 50,000 each, right?
Yeah.
In the ridiculous extreme, I add 100 million curly-haired dogs, and now my data set is 99% curly-haired dogs, and that's not going to be a good result. So yes, in that vein, like what you're
So
asking.
maybe it's like also like more an art than science.
Yeah, so I would say, adding a small amount is generally pretty safe, but you still do have to evaluate, because as with anything, the coverage and diversity of your training set, matters. And so when you're doing things, if you're putting your thumb on the scale, it potentially could have an impact. Yeah, I see a hand raised.
Hey Ted, I was listening to you talk about the Kaggle competitions and how it's kind of the assumption is that the data is, already kind of pre-processed or it's like bundled up and ready to use and send. And then you were talking about how you might make the decision to go acquire more data and it might be labeled differently. And I'm wondering, how do you reconcile that difference in the data labeling? Would you run a model on the data to like figure out how to label the data sets consistently, or how would you approach that?
Yeah, it's a great question. I don't want to take too much time. We still have actually a fair amount of material in this chapter, but basically, super simplistically, right? You can add the data and retrain your model, and then see whether your public leaderboard performance actually goes up or not. And typically, the data you get off the internet won't be exactly the same. There'll be a little bit of domain shift. And so at first, usually your performance does not go up on the public leaderboard or on your internal validation. And so then the question is, am I going to spend time figuring out what's different about this and compensating for it or correcting or scrubbing or doing whatever I need to do? Is that worth my time, or should I spend my time on other ways of improving the model? And that's why in the end, I don't think you see all that often where people successfully pull in external data in order to do really well on Kaggle competitions. I think part of the nature of that is that the sponsors of the competitions, if they knew there was tons of really great close enough data out there, they would have already used that. And so if you're sponsoring a competition, it takes time, energy, money, prize money, whatever. And so they're already sort of factoring this in, and they're giving you hard problems where there isn't such wonderful data available. That'd be my sort of short answer, but it's a cool question. All right, so I'm gonna move on for the sake of time. So then after we spent a lot of time talking about k-means just as sort of our straw man to understand clustering and things like that. Now we're going to kind of go fairly quickly through these other algorithms. The author mentions dbScan, and I haven't used dbScan that much, but there's this idea that you have this epsilon that says, what are my neighbors? And dbScan is very different from k-means. K-means just cares about distance to the center. dbScan is sort of the opposite. dbScan doesn't care about distance, it just cares about its neighbors. And so if you have a cluster that just has very continuous density, no matter what the shape is, it could be a total worm-like shape, as long as there's like nice high density within the worm and low density outside the worm, then if you choose the right epsilon, every circle is going to have a few neighbors in it, and they'll all connect, all the circles will connect together, and then any other clusters, any other worms will be outside of your circles. The problem is, what exactly is the size circle you should pick, and that seems to be a real pain in the neck. In real data, your worm might not have super even density throughout, and so if there's any low density regions, then the worm might get chopped into different segments. So there is a variant that the book just very lightly mentions, HDBScan, and I don't understand it fully, but basically, whereas in dbScan, you just draw a circle, HDBScan is kind of looking at if I drew smaller and bigger circles, how would that affect the number of neighbors that I have? And it's trying to more intelligently look at that. And so it's able to be a little bit more adaptive and say, in this region around this particular data point, things are generally kind of very sparse, and so in order to go from 3 neighbors to 5 neighbors, I need to go this big distance. But in other areas where things are very dense, then it may say to go from 3 neighbors to 5 neighbors, it's this only microscopic change. So it's a little bit more adaptive, and then it does the same thing where it kind of merges the circles together. The book says that it's not available yet in Scikit-Learn. It looks like fairly recently they did actually add it to Scikit-Learn, and so there's a nice page that I found. The go away zoom menu, thank you, where they have some visualizations, and they say, like, here's this tricky clustering problem. You can see these are not circular, and they kind of touch each other, and it's not really clear. And then they show different algorithms, what they would do. So k-means doesn't seem so great because it has its circular assumption. And then you'll be completely shocked that the HDBScan documentation says that HDBScan did the best on this clustering problem. Shocking, I know. But it actually did do what seems to my eye a pretty intuitive job. Yeah, maybe they chose this example specifically because their algorithm does really well on it. You also see here where all these gray points are not assigned to any cluster. It's a very different feel than k-means. And so all these things around the outside are not affecting when it's building these worms. Whereas k-means would say, I have to assign this guy here in the lower right corner to a cluster. Which cluster should it be? Blah, 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 blah. Yeah. So any region that's low density, it just sort of says you're not part of a cluster, which, again, depending on your use case, you may or you may not want that behavior, but there is an intuition where I can say, yes, I just want to know where there are my dense clusters and everything else is just background.
Good for politicians.
All right, let me check the chat and see if there's important or if it's chit chat.
Yes, concepts in their head and then band
All right,
together.
seems like people are talking about external data, so I'm going to keep going. All right, so HDBScan is I think an interesting algorithm, and then the last part of this part on clustering mentions here some other algorithms Some of them don't scale very well to large data sets. I don't think they're that popular. I kind of like the agglomerative clustering. I wouldn't use it for everything, but the cool thing about it is it doesn't give you just like a single answer. It just basically slowly merges points together into bigger and bigger clusters, and in the end, all of your data is just in one cluster. Okay, so it starts with, if you have 10,000 data points, you have 10,000 clusters, and in the end, you have only one cluster, right? And you can kind of pick any point in between, depending on whether you want lots of small clusters or you want few big clusters, and you can visualize it to the extent that your data is not too big in this big tree, what they call a dendrogram. So for certain use cases, I think that this is actually kind of nice, and it lets you, again, it lets you choose different levels, so so that kind of makes sense. The other algorithms, many of them don't scale, and Scikit-Learn has some really nice high-level documentation pages. So like if you're doing clustering, if you're doing different tasks, and so they have one, and then you can see here, they show you, 6 different data sets that look very different, and what each of these different algorithms did with certain parameters. So you have to understand these algorithms can give you different results if you have different settings, but they show you some example things. And so if we just look at k-means on the far left with its circular preference, then you can see that sometimes, like for these top 2 rows, this data is just so completely not circular. It's never going to do well, but some of these other ones can kind of follow the density, and they can give you these more worm-like, or in this case, these concentric circles. It actually can get that right. All right, so for time, we're going to move on to Gaussian mixtures, and Gaussian mixture models. Hopefully, you were able to follow. The book does not explain it in extreme detail how they're calculated and all that, but the idea is that Gaussian mixtures is a probability density estimation algorithm, and knowing the probability density is sort of overkill for most things that you want to do, okay? And so most of the things that you do are a subset of that. So for example, if you are looking for anomaly detection, okay, you can just simply say, if it's high probability, it's probably not an anomaly, and if it's super low probability, that's where we're going to inspect it further to see. The problem is that Gaussian mixtures do not scale to very large problems, to very high dimensions. And in fact, the reality is there is no algorithm that scales to high dimensions, okay? You cannot, if you have what's today considered a small language model, okay, and it has 500 million parameters, you cannot solve a 500 million dimensional probability density function. Even if you were just looking at values, I'm just saying 500 million. So even if you're just looking at floating point numbers between 0 and 1, which you're not, but let's just say hypothetically you constrained it to just check 500 million dimensions of floating point numbers between 0 and 1 is just combinatorially impossible. If you know the probability density, you can build a generative model, because just like in Python, if you want just say a 1D Gaussian distribution, you can say generate random numbers from a Gaussian distribution. That's what knowing the probability distribution lets you do. So you can do that with Gaussian mixtures too. We would love to have that, and so you could have this for cat and dog images. You could say, here's the distribution of all possible dog images, but it's just, it's intractable. And so in fact, what you see is that all of the powerful generative models. So whether it's language models, diffusion models for generating images, they are not actually density estimation models. That's too good to be true. It's impossible. It mentions that this expectation maximization algorithm is used to calculate Gaussian mixture models, the solution for it, okay? And I just wanted to mention that EM is actually a powerful algorithm. You'll see it pop up in other places. So it is not specific just to Gaussian mixtures. EM is a general algorithm under certain conditions, basically, and they make the analogy that it looks a lot like the k-means algorithm where you alternate between these two steps. Under certain conditions, you can be guaranteed convergence. And so under those conditions, EM is pretty great. So I actually was not, I would have flunked if you had asked me this question before rereading the chapter. What's the difference between how you set up anomaly detection and novelty detection? And so then the book made it clear and helped remind me. For anomaly detection, you train on the full data. So it includes your outliers, and the outliers are relatively rare. For novelty detection, you want to train just on all of your clean data, your non-outliers, and then that makes the outliers hopefully pop a little bit more in terms of their even lower probability. If you had, for some bizarre reason, lots and lots of outliers in your training data, then those outliers would actually just be considered reasonably high probability normal things. So in a lot of problems, it probably doesn't make a difference because the outliers are rare enough that they're not going to get any appreciable density. But I thought it was a good just distinction about that. So if necessary, you can just do a two-step thing where you do some sort of algorithm. You find the lower density things, you treat them as outliers, you throw them out of your data set, and then you train it again. We have another thing here in terms of how would you select the number of clusters in a Gaussian mixture model? Life's even worse than k-means. There's not a great way to pick the right number of clusters for a Gaussian mixture model. And there's a sidebar box that talks about how can we have probabilities, or more technically precise, how can we have likelihoods to help guide us. And so I'm not sure how much people have seen sort of the formalism around likelihoods. I recommend go reread this box in the book where they talk about the difference between probabilities and likelihoods. This is certainly not a complete statistical treatment of what is a likelihood function, okay? But in practice, I think 99% of the time, you're going to see the words used the way that this box describes it. So most of the time, when we talk about the likelihood, what we're going to say is, given the data, and we sort of freeze the data, which model would have the highest chance of producing that data? And when you're talking about probabilities, we're usually using the term the other way to say, for a particular result, given a frozen model, what's the probability that I would actually get that particular outcome? So if I'm doing anomaly detection and I have network traffic that I'm monitoring, okay, and I see this particular pattern of network traffic, then I would say, what's the probability that this is like regular network traffic? And that's given a certain model, what's the probability of this particular input? And if it says, well, I've never seen something that looks like this, is really rare, then that's an anomaly, and you probably want to investigate it. What could it be? Well, it could be that ChatGPT was launched yesterday, and all of a sudden there's all these hits going to this site that you've never seen before, or it could be a virus, somebody's trying to attack your network. Doesn't for sure mean it's a bad guy, but it does mean it's different than what you've seen in the past. Okay, so the likelihood says, hey, if I have certain modeling assumptions, my neural network, my Gaussian mixture, my linear regression is only capable of producing certain kinds of models, then what value of the parameters would say that, so if I have a particular set of parameters, it says, oh, the chance of you getting this set of 100 inputs is 1 in 1,000. A different model says the chance of you getting this set of inputs is 1 in 1,000,000. Well, then the 1 in 1,000, you would say, is more likely a fit for your data than the one that's 1 in 1,000,000. And so this is the whole maximum likelihood estimation business, okay, where we're looking for the set of parameters that gives us the greatest chance of producing this data. It's an estimate. It does not mean that these parameters are right. It just means that this is a principled way of choosing this particular set of parameters and not slightly higher or not slightly lower. Okay. The book also mentions that if you're looking for the maximum likelihood, if you look for the log of the likelihood, you're going to wind up at the same point. Okay, because whichever number is the biggest, the log of that number is also going to be the biggest. And it doesn't mention this, but you'll often see sometimes where people will do 2 times the likelihood just because it makes the math easier later on. And it's true that if something is the biggest number, then it's going to be the biggest of the 2 times. You could do the square root. You could do the square. There's a lot of functions you could do on positive numbers that the biggest one will still be the biggest. And so you will see this in ML papers where people will sometimes say it is more convenient to work with the log of the likelihood. It is more convenient to throw a ×2 in there. It's more convenient to divide it by some constant just to make the math easier. Okay. The important thing is that they all have the same set of parameters that give you the mode, the peak on. The other thing I wanted to mention is we haven't really talked about this, but for a lot of these algorithms, we have a loss function that we're optimizing. We have a loss that we're minimizing. That loss function is oftentimes derived from doing some probabilistic analysis of this problem and figuring out what is the maximum likelihood. So it turns out that when we just talk about mean squared error for like linear regression, okay, you could say, well, mean squared error, I kind of get the gist of it in that large numbers, when you square them, get even bigger, so it's penalizing large errors more than small errors. But if you want to penalize large errors, why don't you cube the error or fourth power it or some other function, y squared or whatever, okay? And in another way of looking at this, if you assume that your input data has Gaussian noise, it turns out that that noise falls off, the probability of being a little bit higher or lower falls off with the square of the distance, okay? And so if you then do a statistical analysis and you say, what is the maximum likelihood for data points where we assume Gaussian noise, it turns out that if you minimize the mean squared error, that will give you the maximum likelihood, right? So one of the things that I've talked to beginning data science people is that theoretically you could say, I'll use the absolute value, I'll use the square, I'll use the cube. All of those things actually correspond to different assumptions about how your errors are distributed. So in the simplistic case where you had only 5 data points, all right, and so say 4 of them were 50 and 1 of them was 51. If you use the mean absolute error, then you're going to get a point that's whatever around 50.2 or something like that if you're minimizing that. Use mean squared error, you're going to get a number that's closer to 50. Okay. And so the whole idea is that how much do you weight the relative importance of the number not being exactly where you expect it to be. Okay. They mentioned briefly this maximum a posteriori thing. So we haven't talked about it. If you've done any kind of Bayesian inference, then this is a way of getting a point estimate from the Bayesian analysis. It's the map is not very commonly used. There's some really wonderful properties if you do Bayesian modeling, where instead of just treating this as like a single parameter, my parameter is 0.2, whatever, we just have a probability distribution. You treat everything as a random variable. You have a probability distribution for your inputs, for your parameters, for your outputs. But the computational complexity of doing this, of treating everything instead of as a single floating point number, as an entire probability distribution, it gets intractable very rapidly. And so there's just going to be some small corner cases where you make certain assumptions and then you luck out and that the math sort of, gets really easy. There are closed form formulas, things like that. So I really do like the Bayesian stuff. I haven't spent too much time on it because for practical problems, it seems like, we're not going to solve protein folding using Bayesian techniques because it's just such a ginormous problem. But I wanted to just kind of take a time out and then mention, if you are interested, there are other books like the old classics like Elements of Statistical Learning that go more into the underlying math and statistics behind some of these things. But the key lesson for me is that one typically would not pick any arbitrary loss function just because I feel like it. Those loss functions have actual statistical implications. So whether you chose mean absolute error or mean squared error, one can, if one does all the math, derive what then is your assumption about the distribution of the errors. What kind of measurement error are you assuming if you use that particular loss function? And so it might seem like when you're, say, training a neural network that you could just like, oh look, PyTorch has 17 different loss functions. What if I just randomly try all 17 of them? And there's a reason why people don't just try all 17 of them, is because they would say, well, that assumption about your errors being distributed this way seems very unlikely to match the problem we're trying to solve. All right, so that was my little side comment on maximum likelihood and whatnot. The book mentions some other algorithms for anomaly and novelty detection. And again, Scikit-Learn has a pretty good page on this. And so you can see here's 5 different algorithms and some different data sets and what they sort of consider is in distribution and what is out of distribution. And you'll notice that in some cases, out of distribution can be like holes on the interior. It doesn't have to just be, on the outside. And I just wanted to mention that it seems to me that I haven't done a lot of this anomaly detection, but it seems like isolation forest is a pretty well-performing, pretty fast, easy algorithm. So if you do run into something where you need to do anomaly detection, that's probably a good baseline starting algorithm. So you can run that. It should perform reasonably well in terms of like speed and accuracy. And then you may iterate and improve from there. But like if I was saying, if you're doing a regression problem, linear regression would be a very simple baseline that's fast and easy to do. For anomaly detection, probably isolation forest. I don't know if anybody else has experience and would suggest a different baseline, but it seems like a pretty darn good baseline. All right, we are a little bit over on time. Any burning questions about the material we covered today? All right, I know some people may need to go. Quick mention, so next week, we're basically starting a new book, as it were. We're going to do deep learning, which is part 2 of the Hummel book. And then for those of you who have a minute to stay, I did come up with a question to just sort of extend. You can look at the exercises, but so my question has to do with, the book mentions that clustering can be used for customer segmentation. And one thing I ask is, like, what data would you collect and use as inputs for your clustering algorithm? And in particular, if you were doing customer segmentation for new customers, one approach that people use is they train the clusters using all the behavioral data. So like, how much do people spend and how often between and blah, 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 blah. But they do not include any demographic features in the clusters they build, even though those demographic features often are very strong for building the clusters, okay? And so my question is, why would people leave out these very informative demographic features when they're building the clusters for new customer segmentation? I'm just saying, yeah, like right now. Again, some people may need to go, but.
Maybe it's like, more parameters, kind of like constraints, like it won't let you produce anything. So to make things simple, they probably just did with whatever they found they needed at that moment. But
Okay.
again, that's when all the scaling competitions and everything comes into picture, where like they want to explore other things too, but they don't want to spend their energy on it and have some high resource, like they pay some X amount of dollars, like way more money than some of the scaling competition prices.
Okay, so
They
I'm
don't
gonna
want them to spend their energy on that.
recap that, shorten it, and say, so maybe it has to do with sort of simplicity, complexity, starting simple. Jacques, you have your hand raised. Did you want to take a stab, make a comment?
Can you hear me?
Yes, yes, we can.
So if again, I'm not very, again, still coming to data science, but I'm just thinking about human nature and interacting with people. If you're have customers, you're trying to discover buying habits of individuals, and you don't want to use demographic data because that might skew your results. You're trying to find buying habits of individuals. So you want to get like other types of information, such as, again, frequency and other information from them, maybe not exactly male or female, or if they are, of a certain race or a certain gender. You want to find out if probably one thing you do want to probably find out is age, because that might be an influence of buying habits. You also want to find out what are the things that they buy that could be connected to your product in another sense that could be scoped to that. Lastly, you can find out like if like what your product is used for, and then connect that to a need that they have, if that makes any sense. So say for instance, stores do this all the time. And if you put baby, like diapers next to baby wipes, they will most likely buy those. If you put baking, like a baking products by next to actual sugar and salt and spices, they'll most likely buy that. So you want to group buying techniques together as opposed to demographics in a sense. I don't know if I'm making sense or not.
Okay, yeah, thanks. So that's one comment relating to focusing on the buying habits. I think there's a little more to this in terms of what I was going for. Did you want to add a comment?
I just wanted to mention, because like I've been working on some data that we actually use. First of all, we're not actually implementing the graphic pictures because we were focusing on like causal inference mostly.
So we wanted to know what's the causality between the data points, not yet with the demographics. So this is kind of like maybe narrowing down into first like you mentioned the patterns that you want to discover within the customers, how they are behaving, and then different individuals that later on you will kind of extract with the causality between them. And then afterwards, like you can add demographic features to expand your information, doing the patterns of what areas will be more affected to which are buyers that you will want to focus on. So this is like kind of like the structural way how you will be approaching your problem. So that's what I would add into it.
Okay, I hope you guys could hear that the core of it was focusing on causal inference, and there was also a comment that you could add in demographic features later. Paul, you have your hand raised. Did you want to add anything different?
Yeah, maybe the demographic information is omitted when the model is being trained, but then maybe it's used at a later date to validate the model.
Yeah, okay. So you could train on just this behavioral stuff and then validate. So I'll tell you what it was that I was thinking about when I wrote this question. Okay. So I said this is a customer segmentation model for new customers. So if somebody's a brand new customer, do you have any purchasing behavior for this customer yet? Possibly not. I mean, maybe you have one purchase because they're a new customer, but you don't necessarily have a pattern yet. Okay. So when we talk about what is the data that you will have available at inference time, what you will have is demographic features. But we don't want the demographics to dominate our clusters because a cluster isn't really about 20-year-olds versus 40-year-olds, right? So one thing you can do is you build the clusters based on the buying habits, like everybody said, and then like you guys said, then you go and you see how do the demographics match with the buying behaviors that you saw. So if you found that your 20-year-olds tend to make lots of small purchases, but maybe your 40-year-olds tend to make fewer but larger purchases, then if you're designing a coupon campaign and you know that this new customer is a 20-year-old, you don't know for sure which cluster they're going to be in, and you might use a different clustering model for returning customers that you have a lot of data on, because then you actually know their behavior. But if you have this cold start problem, then one trick is you say, I'm going to separate out the things that I know early on from the things that I don't know, and I'm going to use this cluster model to best guess what cluster someone should be in because I don't have the data yet. And then later on, like people mentioned, you can go revisit this and have a different model for when you have a lot of data. Okay. So again, trying to tie back these algorithms to sort of real world when you're setting up the problem. It's not just, oh, look, in my database, I have all these fields, including age and gender and da-da-da. No, depending on the nature of your problem, you might purposefully say, I'm going to set things up a certain way. And in this case, omit those fields. Yes, Amarnath.
Hi, Ted. So I have a question. In the old world of statistics, we had this thing about having parsimonious models. The idea was that we don't want too many variables, and we just want those variables that give us most of the information. And of course, at that time, we were looking at trying to fit things to the data. So actual models that will, like a linear model, regression model, and stuff like that. And then you have the other end with deep learning, where more data you add, it just basically performs better. There's no question about it. So my question is, when you do these intermediate things that are not really quite statistics in the sense of linear regression, but these clustering things, where would you say we fall in terms of parsimonious versus more data, if that makes any sense?
Yeah, that's a cool question. Thanks. I think that there's a very broad principle of parsimony that always applies. So if I can give you a simple explanation and it performs roughly equivalent to a very complex explanation, then we prefer the simple explanation. Okay. So naively, if you could do clusters and 6 clusters gives you the exact same metric as 29 clusters, you probably immediately just intuitively would lean to the 6. Okay. That's sort of the very broad principle of parsimony. But what I would say is that at another level, parsimony at one time was sort of equated with that when you do something like polynomial regression, you end up overfitting on your data, and so you want to avoid that. What I would say the more nuanced answer in that regard is that yes, we avoid overfitting, but literally parsimony is not necessarily the way we need to avoid overfitting anymore. Now we have many more techniques at our disposal.
Yes. Thank you. Yeah, that's a
All right, great. All right, I think we'll wind things up here. Thanks everybody for joining us. I hope that this was useful to deepen and add perspective to the contents of the chapter. And thanks for everyone for the participation, for the questions. And once again, next week, excited to start deep learning. The 3rd edition book is TensorFlow. I'm going to be talking with Ryan. We're going to come up with a game plan to include PyTorch. I don't know exactly how we're going to do it. The PyTorch book is not yet available in print, but since PyTorch is much more prevalent now than TensorFlow, the plan is to include that. We will not only be doing TensorFlow, but I just don't know exactly how we're going to do it yet. All right. Thanks, everyone.
thank you. Thank you very much.
Thank you.
Have right?
Yeah.
So we have some kind of sorry, I didn't go through the overview and like what are some of the topics you feel like be prepared with kind of thing, so we could ask questions only on that, so that the rest of us could probably prepare the other topics in case a question arises and we could like better answer or maybe a fresh perspective kind of thing. Is that a possibility or?
I'm not really sure for this hands-on machine learning book, which is more introductory level. What Ryan and I decided is that we were going to try to work hard for the two of us to cover all the materials, to make sure that as a beginner, it's hard. There's so much to learn. It's already hard enough. We wanted to try to make sure that we gave people as straight of a line and not as windy of a line to learn the material. But just so you know, in other books, other topics that we do have it be more of a collective learning session. This one's a little different, where Ryan and I are doing a lot more just sort of focusing things.
So would you say this coming book, that the one for the next week, it's somewhat like a corrective one, or it's more like straightforward, like straight line approach?
Knock on wood, Ryan and I will find as straight a line for you to learn deep neural networks with the fewest unnecessary extra things, but just as straight a line to learn the core things for deep learning. Yeah.
And do we have a group or something that we kind of?
Yeah, we have Slack. The reality is people don't use it a lot, but there's actually a book club channel where throughout the week anybody can ask questions or make comments, or if you're like, oh, it talks about this, but actually there's outside of the book, there's this great article by so and so that talks about this. That's actually really nice when people post those, but I think we've had like maybe like, I don't know, in 9 chapters we've had 5 of those.
I will make it a task. I will leave comments in there in the coming week.
All right, awesome.
Thank you, Ted. I just wanted to ask really quick, are you guys still doing the computer vision stuff on the, because I know you do the book club and then the monthly meetup. Are you still doing computer vision on those days?
Yeah, I'm doing the vision on the monthly stuff and just trying to kind of merge it in with everything else we're doing.
I don't have time to read both, but I think I'm going to try to watch the video playlist.
Yeah, and you could theoretically watch the one that I'm basing it off of, or you could watch my recaps of what he's saying. You could decide which is actually, because he actually did a whole video series, and so, you know, my idea was to if we were doing it more as a group, then it would be like, okay, what questions do you have about what he covered? And then it's kind of not really gone in that direction, so then I'm kind of recapping it. And so it's up to you to decide whether.
Those are on the GitHub repo?
Yeah, it's a little bit confusing, but there is, if you look in the README on the GitHub repo, you can see a link to the YouTube playlist where he has all of the videos. And there's also links to, he created Jupyter notebooks where you can play with all of these things. So he did a really nice job, but it just requires a little bit of work. At the time that he did them, he would be like, hey, I have an event and I'm going to talk about whatever, you know, segmentation. And so if you attended the event, then it was kind of obvious that these are the slides for this event and here's the notebook. But now when you just go to the repo, you're like, there's 15 notebooks. Which one switch? Yeah. Yep.
All right. Well, thank you.
Yeah. Cool. All right. Yes. Actually, the easiest thing is it's the same book. It's part 2, so it's technically it's chapter 10, but it's the first chapter of part 2. Yeah. Yeah, I'm talking it up a little bit like it's 2 different books, but it isn't technically. Okay, so if you go to the bottom of the very long description for any of the meetup events, then you'll see, sorry, this is the Slack link.
Okay, I tried looking through the GitHub, I couldn't find it there. So
sorry, yeah. So from the GitHub, there are links to individual events, or you can go to Meetup and just pick one of the events. But
it makes sense having it over here because GitHub, again, the chapter changes, and again, yeah, it may not carry on. Okay, thank you.
Yeah, awesome. Thanks for coming.
Thank you. It's a very interesting way. I think I've seen a lot of these series where the people go on the Twitch streams and they kind of read these books, and there are people who try to explain over the Twitch streams. So this is my first in-person event, and it's pretty cool, asking these questions. But I probably should have cut down my questions on the k-means algorithm. The thing is that you see it everywhere, and you think that it's important. But again, there are other stuff like maybe the HTPC thing that sounded way more interesting, and probably that could be something that we could.
No, don't worry. I love questions, and in fact, one very fun book series would be if there's enough people where they read the chapter, and then everybody has 1 or 2 questions or whatever, and then all we do is do the questions, and we don't actually go through the book in order at all. I would be completely fine with it just being a office hours questions session,
kind of session,
right? You know, so more questions is good. Don't stop asking questions. If we spent the entire time just on questions, I would be thrilled, because basically what I would say is the people who did the most work, who then had the questions, got the most value, and so it just encourages everybody. If you read and you figure out what your questions are, then you will get all of your questions answered. But but it's not about, because, hopefully the author of the book can say it better than I can say it. So just read the book. If you want to know how does K-means algorithm work, read his explanation instead of mine, But if you have questions about his explanation, that's where it's helpful to have a real person who can answer your questions.
Yeah, definitely. I think like reading the book before and during the session, and then after, it's like three parts, and then the time space in between, so you will get a better idea. Like some parts you miss out. Yeah, that's nice. And like the other person was saying, basically when you include more data points, it's like chaos, right? But that's when exactly like growth happens. So I like those things kind of thing where like come up with chaos and then like you grow or you learn.
Awesome.
Thanks a lot for the session.
Yeah, you're welcome. Sorry, I'm terrible with names. Would you remind me your name
sorry,
again?
I didn't introduce myself. My name is Pratya.
Prathya?
Yeah.
Okay, awesome.
And Ted, right?
Yeah. All right, and you are here in San Diego, yeah?
Yeah, I just worked down at Sempra Energy, so they have a data center down here.
Oh, okay.
So I worked there and I stayed closer, so I didn't know that there was something like this going on the weekend.
Awesome. Well, I'm glad you found us.
I'm very happy. Thank you.
Okay.
Well, I hope we have an active Slack channel.
Okay, thanks.
I hope I found you there. Thank you.
Okay. Bye-bye.
Have a good one.
Yeah, no worries.